So I think we can actually go to the next one, which is Milana Vuckovic from the European Center for Medium Range Weather Forecast. I think it's a very similar topic from the first talk that we heard. It's just probably more focused about the climate change and air quality information. So we're really looking forward to your talk. Thank you so much.
Hello, my name is Milana. I work at ECMWF on Hidalgo project, and today I will talk about building cloud-based data services to enable earth science workflows across HPC centers. We have all already learned about Hidalgo in this session, so I will give you a brief introduction to ECMWF, who we are and what we do, and I'll present our data challenge to you. At the end, I will talk about the ECMWF role in Hidalgo project. ECMWF stands for European Center for Medium Range Weather Forecast. We are an international intergovernmental organization. We are operational numerical weather prediction center and also research institution. We are operating 2 Copernicus services, climate change service and atmospheric monitoring service. We are also supporting Copernicus emergency management service. We are based in Reading, UK, but our new data center will be built in Bologna in Italy. From the name, you can already tell that we do weather forecast. Our domain is medium range weather forecast, which means forecast for up to 10 days or 2 weeks in advance. We are also running extended and seasonal range weather forecast, which is from 6 weeks to 6 months in advance. We don't do climate prediction, and what we also don't do is short-range forecast, which is done on much finer spatial resolution and on much more frequent production schedule. This is the domain of our member states' national met services. They are, however, using our output for boundary and initial conditions for their regional models. Our work has time-critical operational component. We are running our model twice a day, one high-resolution model up to 10 days, and an ensemble of 50 members up to day 15. As our member states are running their regional models on a much more frequent production schedule, to support this we have 2 additional model runs every day with shorter forecast lead time and limited number of products. We are disseminating around 100 terabytes of data daily to around 200 destinations worldwide. We also have a non-time critical component, which is a research within the center, which is constantly updating and improving the model. All of this data produced by our operational and research activities is then archived, and the archive is currently holding more than 300 petabytes of data, and it is the biggest archive of its kind in the world. At the moment, we have 2 Cray supercomputers which are identical. One is operational and the other is a backup and used for research. So if anything happens during the production, one can relatively easily switch to the other. We also have cloud services, which we started building up in the last few years. We are running Copernicus Climate Data Store operationally since 2018. And together with EUMETSAT, we are setting up European Weather Cloud, which is now in the 2 years pilot phase. And together with EUMETSAT and Mercator Ocean, we are involved in Wikio Cloud. As mentioned before, we have our tape archive library with around 140 drives where we archive the data we produce. This brings us to the data challenge. On this first graph, you can see the historical growth of our disseminated data. Only 5 years ago, this was in the order of about 5 terabytes, and right now we are at around 30 terabytes, and this is only going to grow further and growing exponentially. If we have a look at the projected volumes of our daily operational and sample data with planned increases in horizontal and vertical resolution, we can see that we are now at 71 terabytes, but in the next 5 years, it will potentially grow to above 900 terabytes. Another problem is that no user can handle all that data in real time, and unfortunately, a lot of ensemble data goes unused. Because of this, we are continuously looking for ways of trying to encourage users to use more and more data, but it is becoming more of a challenge. Another problem out there is that our methodological users are used to our data, but these domain-specific formats and conventions are not something users from non-methodological domain are familiar with, and that is not making things easier. We do have sophisticated dissemination system to push real-time data to the users, and we are providing web services to allow users to get the data this way too. But the key challenge here is how can we improve users' access to such large volumes of data? How can users access data today? Today we have something called ECMWF Web API, which allows users the access to our public or restricted data sets. Our users from national med services and commercial users can access the full Mars archive, and self-registered users can access public data sets. Once a user has an account, they can install ECMWF Web API and submit a request. Here we have our specific retrieval example where you would specify methodologically meaningful parameters. So precisely what data are you interested in, what area, for which dates, and then you retrieve it in formats like netcdf or grep. And here are the links if anybody wants to try. Another way to access some of our data is Copernicus Climate Data Store. It is only data produced for Copernicus Climate Change Service, so mostly climate reanalysis, seasonal forecast data, but also some satellite observations. Because some users might need to work with amount of data that would be too large to download and then process, CDS is also offering a toolbox where the user can process the data before downloading it. User can also use the toolbox to make specific applications hosted at CDS. All this data on CDS is open and portal is free to use. But we need to find novel ways of using this data. So how our data flow looks now, we have our HPC, it is producing the data. The data is then goes to our fields database or FDB, which is our dedicated object store for meteorological data. And that is basically where we store it immediately after production. Then it goes to disks and tapes. But we want to change how we see things. We see our data as one big hypercube that we would like to provide to people to access in the environment that is more in the control of the user, but hopefully closer to our data. So we want to move the compute and not the data. Keep the data where it is, mainly because it is getting too big, and bring the computation to the data because compute is getting cheaper and data storage is not. So Hidalgo and ECMWF. Hidalgo is Horizon 2020 project with its collaboration with across 13 institutions across 7 countries. The vision is to advance technology to master global challenges, and the mission is then to develop novel methods to HPC and HPDA and so on, and to simulate the complex processes involved with these global challenges. So bridging the gap between how we produce the data and what then we do with the data. Our role in the project is to enable coupling between 2 pilot applications, so human migration pilot and urban air pollution pilot and our weather data. And you have heard more about this coupling work from Sergey in this session. ECMWF role is to enable coupling as means of how to build a workflow. If you think of a spectrum where you could do the data analysis, you could do it on our HPC, but because we are running time-critical operations on a tight schedule, our HPC is actually closed system. We could do it in a public cloud, but that would mean reducing the data set, not input all the data to the cloud. So the idea is actually to build a cloud, to build a private cloud, and creating a cloud that is at ECMWF, just next to our supercomputer. And then user can bring their workflow and they have very fast access to the full data set. So the key point here is that we want to give some sort of access to our closed HPC system. And this experience with such workflows could be useful model for other HPC systems around Europe who have similar restrictions regarding the access to the HPC. Hidalgo, we are collaborating with two HPC centers, so HLS from Stuttgart and PSNC in Poznan, and our cloud facilities will then be connected to these two supercomputers. We have two stages in our work here. First part is what we call static coupling. These simulations have not taken into account our data. So the first stage of the project is for them to take the static reanalysis data, which is historical weather data, to analyze them and to see how it can be used to integrate and improve their own simulations. In the meantime, we are building the new API to access the data from the cloud. And this part is mostly completed. In the second part of the project, we are concentrating on using the cloud and the REST API to use data while it's hot, because weather forecast becomes stale after only less than 12 hours, and when it's replaced with a new, fresh forecast. We are using also experience from building the climate data store too. So we want a system where we can bring the user closer, provide them with the computing resources, so move computer to the data. So where we are now, we have two systems, one to push the data to the users, and the other to pull the data from the archive. We want to have a hybrid system, a platform where you come to the cloud, spin up your virtual machines, and bring your workflows in. You can access the data as a service. You could also access our hardware directly if you want to control the infrastructure, to be in control of the infrastructure. The service that we've been developing, Cloud Data as a Service, is called Polytope. It is deployed at ECMWF and accessible externally. It exposes a RESTful API, and we are providing CLI and a Python API. It will give the user access to Mars or whichever dataset the user has permission to access. So how it works, the user submits a request, they can pull to see the status of the request, and then when the request is done, the service we've been developing, Cloud Data as a Service, is called Polytope. It is deployed at ECMWF and accessible externally. It exposes a RESTful API, and we are providing CLI and Python API. It will give the user access to Mars or whichever dataset the user has permission to access. So how it works, the user submits a request, they can pull to see the status of the request, and then when the request is done, they can download the data. The system is built to be scalable and also deployable outside of ECMWF, but all the complexity of the system is hidden from the user. For them, it's just a web API.
Thank you so much, Milana. If is there any question from the audience, we can open it up. Otherwise, I can come up with a question. Can you hear me, Milana?
Yes.
Hello, hi. Well, very nice talk. Thank you so much. And let me ask maybe a naive question, because I'm not a particular of the field, but I also work with computational simulation. So I suspect that the work that you're doing basically implement a huge amount of data, and so you basically run a very, great amount of simulation. Did you guys partner with anyone like doing a parallel computing, or you just don't need it?
Well, we have our own HPC, so we are running everything there. But we are part of many European projects where we cooperate with people and then explore whatever new technologies. So, but yes, we are actually running things on other supercomputers. If that is
okay. I remember once the iccs was based in when we did it in China. I remember that we visited this facility and they had a very big supercomputer over there. I heard a lot of parallel computing technique. So Okay, good, very good. Thank you so much. Thanks again. I think that I can try to see if Zoltan is online. Zoltan, can you hear me?
Hi, Stefano. Yes, I am online.
Stefano,
Hi,
sorry, there are two questions to Milana.
Oh, I'm sorry. I'm sorry. I didn't see them.
Sorry, I didn't see them either.
Okay, so I'm gonna read them for you. Thank you for whoever make me notice this. So we have one question from Lawrence Lin. If you can comment on your plans for compute to data. So how will that be implemented? If you have any concrete technology in mind.
So we are building a private cloud for that, which will be together with EUMETSAT. So the users will be able to access both satellite data and our data, and then the data will be pushed there right away.
Okay,
So
thank you. Let me ask you the second question, which is from Anton Lebedev. Has there been any consideration to reduce the amount of data rather than to try and push petabytes to users to have them to do something with it? So specifically reduction of the data set to minimal subsets.
Yes, every user can actually specify what they want to get. So they are not getting everything. Every user has their own dissemination or archive request where they can use only a subset from the data. So no user is actually downloading everything. We are not, but we will push everything to the cloud, and then from there users can select what they need. But we are also processing some data, so users can get some process data too, especially the ensemble.
Okay, I think we can continue the discussion on the question and answer section. So Milana, thanks again for your talk.